Welcome to PCB Fundamentals at Iron Wolf Academy. In this course, you are going to build a solid mental model for how modern electronics are constructed. Instead of relying on traditional point-to-point wiring, you will see how etched conductive traces on a non-conductive substrate make complex circuits possible. Across these 15 sections and 22 slides, we will cover three main practical skills. You will learn to evaluate whether a design requires single-sided, double-sided, or multi-layer board construction. You will understand the chemical etching process that turns copper into functional parts. Finally, you will learn to trade off mechanical strength against component density when choosing between through-hole and surface mount technology. To kick off Module 1, we are looking at the substrate and the trace. The term printed circuit board can be a bit misleading because you might picture ink being applied to a sheet of paper. What you are actually working with is a solid insulating board that has physical copper pathways etched into it. Understanding this distinction is crucial as you start working with hardware. It is not about printing conductive material onto a surface. It is about taking an insulating base clad in copper and removing what you do not need to leave your parts behind. That structural reality shapes everything about how these boards function. Let's talk about the foundation of your board, starting with the substrate. Most standard printed circuit boards rely on FR4, which is essentially woven fiberglass held together with epoxy resin. This creates a solid, rigid insulator whose main job is to keep your copper layers physically separated, preventing short circuits across your board. While you are probably used to seeing boards in that iconic green color, that outer coating is actually optional and comes in various colors depending on the manufacturer. The crucial takeaway here is that you need to carefully choose your underlying board material up front, well before you commit to a finished design. When you look at a printed circuit board, it is easy to imagine the copper as just a thin coat of paint, but it is actually a solid metal skin permanently fused under intense heat. This copper foil forms a tight, robust bond directly with the insulating core beneath it. As you move into complex multi-layer designs, these thin conductive sheets are carefully stacked on top of one another inside the board. It is this lamination process that really matters because the overall mechanical strength of your entire board relies on how securely these bonded sheets hold together under stress. To really understand modern circuit design, you need to stop viewing the board as just a flat sheet of metal and start picturing it as a fully planned city map. Old school, bulky wiring used to clog up devices, making it impossible to fit components into sleek modern enclosures. We solved that through chemical etching, which carves precise microscopic paths where thick copper sheets used to sit. By replacing those heavy, tangled wires with flat, thin traces, we can route power and signals through minimal space. This transition is the single biggest reason every compact gadget you use today can actually exist. Now we're moving into Module 2, where we focus on how circuit patterns are physically manufactured. When you imagine printing a circuit, it is easy to picture traditional printing, like running ink across a page. But making these microscopic circuits requires a completely different approach. In this module, you will learn that we do not use ink at all. Instead, these intricate patterns are defined through a precise combination of light and chemistry. By shifting your thinking away from standard printing and toward photochemistry, you will understand how these tiny, complex structures are accurately formed and brought to life. To understand how we manufacture these circuit patterns, think of photolithography like developing an old school photograph, only we are creating metal traces instead of an image. It all comes down to precise light control using masking. We place a mask over a layer of photoresist to selectively block photons in specific spots while allowing them to hit others directly. When ultraviolet light shines through, it acts as a stencil, defining your circuit paths by altering the chemical state of the photoresist underneath. Finally, chemical development washes away the copper where that exposure changed the material, leaving behind the exact physical pathways your design requires. Chemical etching is where your circuit pattern really comes to life. During this removal stage, the entire board goes through an aggressive chemical bath. The acid selectively eats away at the raw metal, causing all the unexposed copper to dissolve completely into liquid waste. The key here is the protective resist layer placed over your design. Because the acid cannot break through that resist, The copper underneath stays perfectly solid and intact. That precise contrast between what gets washed away and what gets protected is what converts a plain sheet of conductive foil into the intricate electrical pathways required for your finished circuit board. As we continue through manufacturing the pattern, a key step to focus on is the solder mask layer. You are likely used to seeing the distinct green coating on a circuit board, but it is much more than just a cosmetic finish. That layer plays a vital protective role by keeping the underlying copper safely shielded from the surrounding air. If you do not have this mask covering your board, your design becomes extremely vulnerable. Without this shield in place, simple exposure to moisture and heat would quickly degrade your circuit performance. Applying this protective coating is what keeps those elements from undermining your work. Now we are stepping into Module 3, which focuses entirely on vertical connections made using vias. When you deal with stacked layers, electrical signals cannot simply remain on one flat surface. They need a designated pathway to move vertically from one layer to the next. That is where plated holes come in. In this module, you will discover the exact way electrical signals travel through these plated openings to reach different levels of the stack. Understanding how this vertical movement works is essential because it explains how separate stacked layers are tied together into a single, fully connected electrical system. Let's dive in and explore how vias make these vertical connections possible. When you are working with multi-layer boards, vias are what make high-density routing possible. Think of them as drilled plated tunnels that bridge your inner copper planes directly to the outer layers. As your signals travel through the board, these plated holes allow them to pass vertically up and down without breaking electrical continuity. That vertical freedom is essential because it lets you route far more complex circuits across multiple stack levels than you ever could on a single plane. Just keep one critical distinction in mind as you design. Do not confuse a simple mechanical hole with an electrical via, because only the electrical via actually carries your signal through the stack. When you are building vertical connections across your board, it helps to picture the whole walls as a functional pipe rather than just an empty tunnel. The method you use to form those wires determines whether electricity actually flows between layers. Plated through holes create a continuous metal pathway along the inside walls, directly bridging your copper planes so signals can travel vertically. In contrast, mechanical wires frequently lack this unbroken electrical link altogether, which leaves your layers disconnected. Ultimately, whenever your circuit relies on vertical signal flow to function properly, you must choose plated through holes to guarantee that continuous electrical path. Think of your circuit board as a multi-layered sandwich, where essential connections happen directly between the slices. When signals need to travel between separate copper layers, they move vertically through plated holes. This capability for vertical routing is crucial because it allows different places to cross paths on separate levels without creating any electrical interference. Instead of being restricted to a flat two-dimensional surface, designers are able to take full advantage of this third dimension. By routing signals vertically throughout the board, you gain the freedom required to pack far more circuits into much smaller spaces than would otherwise be possible. Welcome to Module 4, where we shift our focus to mounting component packages. In this section, we are going to compare the different mechanical attachment methods used for standard components like resistors and chips. How you physically secure these parts to a board directly impacts how tightly you can pack your overall layout. By evaluating these attachment techniques side by side, you will see how mechanical constraints translate into real-world density limits. Understanding these physical boundaries will help you grasp what ultimately caps component spacing and how these mounting choices define the maximum density you can achieve in a design. When you insert component leads straight through the board, you are creating deep, rigid anchors that give the assembly exceptional resistance to physical vibration. Instead of mechanical stress pulling on delicate surface pads, that energy gets routed directly into the full solder joint structure. This physical locking mechanism is why heavier components stay completely secure. Their pins brace right against the inner walls of the drill substrate. In practice, you will often encounter hybrid boards designed to take advantage of this exact strength. They use these robust through-hole connection points to anchor high stress or heavy parts, while keeping the surrounding area clear for dense surface mount tech. When you look at modern electronics like your smartphone, the level of complex integration inside is incredible, and surface mount density is what makes that possible. By soldering components directly onto surface pads, instead of relying on traditional bulky leads, you eliminate a massive amount of wasted space right off the bat. That shift allows us to dramatically tighten the spacing between parts, fitting significantly more components into every single square inch of the circuit board. Ultimately, achieving this level of density is the primary driver behind modern device miniaturization, allowing us to pack immense capability into increasingly smaller, thinner packages. When you use hybrid assembly strategies, you are balancing mechanical strength with component density. Connectors often experience significant mechanical stress, so you want their leads passing completely through the rigid substrate material to anchor them securely. On the other hand, automated lines can place tiny chips directly onto pads without needing drilled holes, giving you high component density on the board. The key to making this hybrid layout work comes down to spacing. As long as you maintain generous clearance between large connector pins and adjacent chip pads, you make it virtually impossible for an unwanted solder bridge to form and ruin the board during assembly. Now we are moving into Module 5, where we focus on material selection and understanding physical limits. As you design and prepare for manufacturing, keeping temperature ratings in mind during soldering processes is absolute key. Excess thermal exposure can compromise your board if you push past what your chosen materials can handle. In this section, we will also tackle the actual reality of working with flexible boards. Flex circuits behave very differently under heat, presenting specific trade-offs you need to account for. By evaluating these material limits upfront, you can select the right options and protect your design throughout the entire assembly process. When choosing your materials, you need to pay close attention to the glass transition temperature, or TG, which functions just like a boiling point for your substrate. Understanding this limit is critical because standard boards will actually soften before lead-free solder even reaches its melting point. If that happens, your board will lose its shape. To survive those reflow conditions, you must use a high-temperature resin that prevents severe warping under extreme heat. To guarantee your assembly stays flat and fully intact throughout the entire soldering process, make sure you specifically select a board material that is rated above 180 degrees. When your design demands tight curves or continuous movement, standard rigid boards simply won't survive. They crack under that kind of mechanical stress. That is why you need a flexible alternative like polyimide. The key difference lies in the material structure itself. Polyimide bends smoothly without breaking because it completely lacks the rigid fiberglass reinforcement found in traditional boards. By eliminating that fiberglass layer, you get a material that comfortably endures bending motions. You should choose this flexible substrate whenever you're designing for wearables or components with moving parts, giving your circuitry the freedom to flex where standard boards would fail. When you place manufacturing orders, using precise terminology is your best defense against critical errors. Industry standards strictly separate the physical state of a bare board from a populated one, and understanding this distinction is essential. A board that consists solely of etched copper on its substrate is officially classified as a printed circuit board. The moment you begin mounting components onto that board, its state changes entirely, transforming it into an assembly unit. Because industry standards distinguish between these two states so strictly, getting your terms right guarantees that your suppliers understand precisely what stage of manufacturing you are ordering. At Iron Wolf Academy, everything comes down to one core concept. You do not need to overcomplicate circuit board design once you grasp this fundamental shift. Instead of thinking in terms of traditional point-to-point wiring, your main goal is to construct a clear mental picture of how a board actually functions. You are using a non-conductive substrate base and relying on conductive traces to carry your signals. That simple framework is the foundation of our entire model. Once you truly visualize how these integrated traces replace standard wiring on that base material, you have the key to understanding the rest of the course.